Hey everybody, Mr. Heier. We're going to look at, sorry, I'm moving my picture into the corner there. We're going to look at kinetic and potential energy today. All right, this shouldn't be very long. You should take these notes real fast. All right, so we're going to start off with potential energy. Potential energy is like stored energy. Example shown here, guy pulling back a bow. When you pull that bow back, energy is stored, and when he releases it, it does work on the arrow pushing it forward. You can do the same thing if I lift something up. I lift something up to a certain height. Then when I drop it, it's going to fall back down and be able to do work on stuff. Okay, it's basically the energy of position. Right? And then the amount of potential energy possessed by an object is equal to the amount of work done in supplying that energy. So going back to the bow, as you pull the bow back, you're doing work on that bow, giving it potential energy. And then when you release it, it releases that same energy to cause the arrow to move. All right, so you pull the bow back 0.5 meters with a force of 100 newtons. What potential energy does the arrow possess before shot? Well, we just said that the work done is equal to the potential energy. So the work is just force times distance. So the work is just going to be 100 newtons times 0.5 meters, and the work is going to be 50 joules. And therefore, the potential energy is going to be equal to 50 joules. And that is our answer. All right, so gravitational potential energy. This is the type of potential energy we're going to be talking about in this unit. All right, we know that potential energy is the work done. So gravitational potential energy is work done against the gravity. So the force is going to be the weight, or mg, and the distance you move it is going to be h. All right, so potential energy is just m times g times h. That goes in the box. All right, mass in kilograms. G is our 9.8 if we're on the Earth. Height is in meters, and our potential energy, just like work, is in joules. All right, so let's do a couple of examples. 5-kilogram object is lifted 10 meters. How much potential energy does it possess? Now possess, so we know potential energy is mgh. That's going to be equal to 5 times 9.8 times 10. And so that's 50, giving me 490 joules of potential energy. This one, um, 1,000 Newton wrecking ball is lifted to a height of 25 meters. What is the potential energy? Now, again, potential energy is equal to m times g times h. Now, careful here. We're given newtons, all right? So that's 100 newtons. That is the weight. That is mg already, isn't it? So that's the force that I'm going to have to lift it with. So it's going to be, this is just going to be 1,000 times 25, or 25,000 joules. Right? If you're given the mass in kilograms, you're going to multiply by 9.8. But if you're given already the newtons, that is the force. So that is mg. And then the second part of the question is, how much work is done in lifting it to this height? Well, we said the potential energy is the same as the work done moving it, so it would be 25,000 joules. All right, so let's look at a factor question. All right, if a car is lifted twice as high in a repair shop, how much more potential energy would it have? All right, or twice the mass, or twice the mass. So let's go potential energy is mgh. Right? If I double m, so I'm going to put a 2 above it, g and h stay the same, so I put 1 there. So the left-hand side of the equation is 2. So the potential energy would be twice as much. All right, so 2 times. All right, same thing if we do twice the mass. Right, because potential energy again equals mgh. Okay, and so again we're going to double we double the height, then these two stay the same, so it'll be again 2 times as much. And if we double both of them, then we put a 2 above the m, a 2 above the h, and that becomes 4 times greater. All right, kinetic energy. All right, kinetic energy is the energy of motion. Right? It has to move in order to have kinetic energy. Okay? The equation for it is 1/2 mv squared. We put that in our box. 1/2 the mass times the velocity squared. So you can see that the velocity has a really big impact. Right? And it has to be moving. And obviously it has to have mass, but everything that has matter in it has mass. So, right, so calculate the kinetic energy of a 3 kilogram toy car that moves at 4 meters per second. So KE, 1/2 mv squared. So 1/2 times 3 times 4 squared. 0.5 times 3 times 16 is 24 joules. And again, the unit for kinetic energy is joules, just like the unit for any type of energy. Okay. What if it had twice the velocity? All right, so kinetic energy is equal to 1/2 mv squared. Right, so if I double v, I square v. So what is doubled squared? What is 2 squared? Kinetic energy will actually become 4 times as much. But if I double the mass, then the kinetic energy only becomes 2 times greater because you don't square the mass. Right? So the velocity has a bigger effect. Right? And you could just plug that number. If I double it, put in 8 instead of 4 here, you'd see that the kinetic energy would become 4 times greater. All right, let's do one more at the bottom of your page. I know this one isn't on your sheet, but you can still do it. All right, so a 1,200 kilogram car gains 4,000 joules of kinetic energy as it accelerates from rest. How fast does the car go? So again, kinetic energy is 1/2 mv squared. Right, so kinetic energy is 4,000. 1/2 times 1,200 times v squared. That gives me 4,000 is equal to 600 times v squared. Divide both sides by 600. Y'all pause and do this on your own to make sure that you know how to do this. So I get v squared is equal to 6.67. And we take the square root of both sides. So I get v is equal to 2.58 meters per second. And that's my answer. All right, so I want you to practice some of the practice problems. All right, tomorrow you're going to have a chance to kind of catch up with everything. All right, so by the end of the day, by Monday basically, but hopefully by the end of the day tomorrow, you'll have the lab completed from yesterday. We're sliding things down a ramp and looking at how much work is done, and look at the change in potential and kinetic energies. We'll do these notes and practice the practice problems. Right. On Monday, I'll answer a few questions, but we're also going to have a learning check over the lab and this new material, and then we're going to move on. All right. Y'all have a great day, and we'll see you on Friday.